Chemistry, the Central Science, Chapter 4, Reactions and Aqueous Solutions, Lesson 4. So one of the ways that we can represent the concentration of a solution is by molarity. Molarity is a number of moles of solute in 1 liter of solution. So if we're going to prepare a solution with a solid solute, we have to know how many grams of that solute we need, what concentration we want it at, and then how much water we want to add. So how many moles of magnesium chloride are present in 60 milliliters of a 0.159 molar magnesium chloride solution? Well, we have to make sure our units match. Molarity is moles per liter, so our volume has to be in liters, so we convert that to 0.60 liters. We multiply by the molarity, see that liters cancels out. Following sig fig rules, which says we have 3, there are 0.00954 moles of magnesium chloride in 60 milliliters of a 0.159 molar solution. How would you prepare 250 milliliters of a 0.707 molar sodium nitrate solution? Well, you have to know how many grams of sodium nitrate you have to measure out. So in order to do that, we have to find the moles. Once again, we convert our volume to liters. And we multiply 0.250 liters times 0.707 moles per liter. Liters cancel, and we find that there are 0.177 moles of sodium nitrate. In order to find the mass, we have to multiply by the molar mass of our compound. So 0.177 times 84.9947 grams per mole, where moles cancel, tells us that we need to add 15.0 grams of sodium nitrate to 250 milliliters of water, and by doing so, we can create a solution with a concentration of 0.707 molarity. Calculate the molarity when we know the mass. We know the mass and we know the volume of solution. So what happens when we add 9.00 grams of sodium chloride to 86.4 milliliters of solution of water? So molarity, once again, is moles per liter. So we need to find the moles of sodium chloride. So we find the molar mass, we divide by the molar mass. So 9.00 grams divided by 58.4428 grams. That cancels out. We find that 0.153 moles. Once again, because we have milliliters, we convert that to liters. Divide our moles by liters to get molarity. 0.153 moles of sodium chloride divided by 0.0864 liters gives us a 1.77 molar solution of sodium chloride. So we can also compare different solutions to see which has a higher concentration of a specific ion. So which solution has the higher concentration of bromide ions? 0.15 molar barium bromide or 0.25 molar potassium bromide? So in solving problems like this, we have to know how many moles of a particular ion are we going to get. When barium bromide breaks apart, you get 1 barium ion and 2 bromide ions. When potassium bromide breaks apart, you get 1 mole of potassium and 1 mole of bromide. So we're basically multiplying our concentrations by our subscripts of the ion that we're interested in. So 0.15 times 2 gives us a 0.30 molar bromide solution, and 0.25 molar times 1 gives us 0.25 molar bromide. So clearly then we have more bromide ions in a 0.15 molar solution of barium bromide. So molarity, and when we figure out how to make solutions when we have solid compounds, we looked at how to do that. Well, what happens when you have aqueous solutions already? Most of your acids and ammonia, they come in stock solutions, and so if you want to have a lesser concentration, you're going to dilute that with water. You add solvent. So what happens then is the thing that changes is our volume. The moles of solute do not change, but what we see is that we have a higher concentration with a smaller volume to start initially, and then we have a lower concentration with a higher volume after dilution, so the final. So we can set up an equality that says MIVI equals MFVF, or M1V1 equals M2V2. So practicing with dilution. Water is added to 25.0 milliliters of a 0.866 molar lithium nitrite solution until the volume is 500 milliliters. What is the concentration of the final solution? So we have to identify our initial set of circumstances and what we're going to. So 25.0 milliliters is your V1, your initial volume, and your initial concentration is 0.866. Our final volume is 500 milliliters. So we plug in our respective values for our variables. And here you do not have to actually convert your milliliters out because they will simply cancel. So we go 0.866 molar times 25.0 milliliters divided by 500 milliliters. That gives us our final concentration to be 0.0433 molar lithium nitrate. So we can see that our concentration went down after our dilution. You have 505 milliliters of a 0.125 molar solution of hydrochloric acid. You want to dilute it to exactly 0.100 molar. How much water would you add? So once again, we identify our initial molarity and volume, and we see that we have a final molarity that we want to get to. So we plug things in, and our M1V1 equals M2V2. So 0.125 molar times 505 milliliters divided by 0.100 molarity tells us that the final volume of our solution would be 631 milliliters. How much water do we have to add? Well, you're always going to go V2 minus V1 to get the V of water. So 631 milliliters minus 505 milliliters tells us that we have to add 126 milliliters of water to our 505 milliliters to get to this concentration of solution. How would you prepare 75.0 milliliters of a 0.200 molar nitric acid solution from a stock solution of 0.400 molar nitric acid? So once again, we're looking at identifying what's our M1V1, what's our M2V2. So the information that's given first is actually your volume and your molarity after the dilution. So those are your M2 and your V2. Your stock solution is always your initial concentration. So that's our M1. So we plug it into the equation. Once again, we're not concerned with the milliliter units. 0.400 molar times V1 equals 0.200 molar times 75.0 milliliters. So we divide the 0.400 into the other side of the equation. We get a volume of 37.5 milliliters of 0.400 molar solution is what we have to start with. In order to figure out how much water we need, once again, we go V2 minus V1. So 75.0 minus 37.5 tells us that we add 37.5 milliliters of water to our 37.5 milliliters of our initial concentration solution to dilute it to get 75 milliliters of the 0.200 molar nitric acid solution. So there's a couple different things that we can do with solutions and solution stoichiometry. One of those chemical analysis is an acid-base titration. So titration is when you are trying to determine an unknown concentration of a solution. And you start with an acid or you start with a base, and it's a neutralization reaction. So you have your standard solution, which is the solution where you know the concentration. So you're using this then to determine the concentration of your unknown. The equivalence point occurs when the moles of your acid equal the moles of your base. So that's the equivalence. The end point occurs when your pH indicator has changed colors. So that's what lets you know that the titration is over. You choose an indicator with a specific pH range of where you expect your neutralization to happen, when that equivalence point is going to occur. And your end of your titration occurs then when the color changes. So as I said, your pH indicators are actually a weak acid-base pair, weak acid-base conjugate pair, and they have different colors depending upon whether there's a higher concentration of acid in solution or base. So the way we set this up is with the burette. You have a flask. Your standard solution goes in the burette. right? Your standard solution is in your burette. Your unknown solution, that concentration you're trying to find, is in here. You start with a known volume. You add a couple drops of indicator. You run your titration until the color changes. So we see that we started out clear, we ended pink. So phenolphthalein was the indicator that was used here. We started acidic and we ended basic. Or sorry, we started acidic and ended basic. So we can also look at practicing with gravimetric analysis, which is effectively a precipitation reaction. And we know that precipitation reactions occur when you mix aqueous solutions together. So how much of a certain substance will I mix with another? What is the amount of expected product I can get? What is the solid that I would get out of it? So there's a couple different things that we can look at with gravimetric analysis. So if 30 milliliters of a 0.15 molar calcium chloride solution is added to 15 milliliters of a 0.100 molar silver nitrate solution, what is the mass in grams of our silver chloride precipitate? First thing we need to do is have a balanced equation. So we're starting with our reactants. We switch partners because it is a metathesis or an exchange or double displacement. We see that we get calcium nitrate produced and silver chloride. So we know silver chloride is the solid because it says it's the precipitate. But we also know by looking at our solubility rules that nitrate ions are always aqueous. So we have to figure out our moles because reactions occur based on the number of things present, not by the mass, not by the molarity, but by moles. And we know that we can get to moles by, mass divided by molar mass or molarity times volume. So we have molarity times volume here, making sure that our units match where we've put this into liters, we've put this into liters. So how many moles of calcium chloride are there in 30 milliliters of a 0.150 molar solution? We multiply those together to see that we get 0.00450 moles calcium chloride. We do the same thing with the silver nitrate solution. We've converted our volume to liters. We multiply to see that we get 0.00150 moles of silver nitrate. So since we have two sets of moles, we have to figure out what is our limiting reactant here. So that's where we use the stoichiometry from the balanced equation to see how many moles of something would we need in order to react. So if we're going to react all of our calcium chloride, it shows that we would need 0.00900 moles of silver nitrate. If we were going to react all of our silver nitrate, we would need 0.000750 moles of calcium chloride. So once again, we're comparing which one do we have enough of. So in this example, we don't have enough silver nitrate because it says that we would need to have this much. The 0.00900, we have plenty of calcium chloride comparing these two numbers. So right, we have more than what we need. We don't have enough of what we would need. So now we go to our balanced equation again and continue with the stoichiometry to figure out what is the mass that we're going to get. So we use our limiting reagent, 0.00150 moles silver nitrate. Our 2 moles over 2 moles comes from our balanced equation. And then we find the molar mass of silver chloride. We multiply everything on the top. We divide by everything on the bottom and see that we're going to get 0.215 grams of silver chloride if we mix these two solutions together. So a sample of 0.6760 grams of an unknown compound containing barium ions is dissolved in water and treated with an excess of sodium sulfate. If the mass of the barium sulfate precipitate formed is 0.4105 grams, what is the percent by mass of barium in the original compound? So the first thing that we do here is just find what is the percent composition of barium in barium sulfate. So these numbers come from the periodic table. This is the molar mass of barium. When we add things up, this is the molar mass of barium sulfate. So we end up with our percentage. Then we look to what did we actually produce? So what is the percentage then of barium in this sample? So we're solving for the grams of barium by using the percent composition that we just calculated. So we divide 58.84 by 100, and then we multiply this times this, right? 0.5884 times 0.4105 to see that there are 0.2415 grams of barium. Once we know the mass of barium, this is the same amount of mass that had to start in our original unknown compound, because the law of conservation of mass says I cannot create or destroy mass in a reaction. So I take 0.2415 grams divided by our original mass of our sample, 0.6760, multiply by 100% to find that in the original sample, 35.72% barium was present. So now practicing with titration, calculate the concentration of a sodium hydroxide solution if 25.0 milliliters of the solution are needed to neutralize 17.4 milliliters of a 0.312 molar hydrochloric acid solution. Once again, we have to have a balanced equation. This is a double displacement exchange reaction here. We're neutralizing, so we end up with water and we end up with salt. Now, when you have a one-to-one relationship, you can simply use this equation, which is MAVA equals MBVB, because the moles of your acid have to equal the moles of your base at your equivalence point. So here we can simply plug in our molarities of our respective compounds. It's a 0.312 molar acid. You have 17.4 milliliters of it. You've titrated it with 25.0 milliliters of your base. So we divide 25 into this side of the problem, and we end up with a concentration of 0.217 molar sodium hydroxide. So now we have to look at what happens when we don't have a one-to-one relationship. Calculate the concentration of a potassium hydroxide solution if 16.1 milliliters of the solution are needed to neutralize 20.0 milliliters of a 0.245 molar sulfuric acid solution. So here, right, sulfuric acid, when it dissociates, you get 2 protons, 2 H pluses, but OH you only get 1. So that means we need double the amount of potassium hydroxide to neutralize our sulfuric acid. And therefore we get 2 moles of water. So here we actually have to do some stoichiometry then. We can't use MAVA equals MBVB. But we know that molarity times volume, when we have our units in liters for volume, gives us a number of moles. So that's what this first setup here is. We're taking our volume and multiplying it by concentration. We then look to what are our coefficients in our balanced equation. So I need 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. If we multiply our volume, 0.200 liters times 0.245 moles of sulfuric acid times 2 moles of potassium hydroxide, we divide by 1, because 1 times 1 is 1. We see that we get 0.00980 moles of potassium hydroxide. We're given the volume. We remind ourselves that molarity is a number of moles divided by volume in liters. So we convert our milliliters to liters to get 0.0161 liters on the bottom. We use our moles that we just calculated. We divide and see that the concentration of our solution that we need is 0.609 molar potassium hydroxide. So what volume in milliliters of a 0.500 molar nitric acid solution is required to neutralize 5.00 grams of magnesium hydroxide? So magnesium hydroxide plus our nitric acid gives us 2 moles of water and magnesium nitrate. This is once again a double displacement. We have 2 moles of hydroxide, so that means we need 2 moles of our protons coming from our acid. So this is basically saying we need double the amount of acid for every 1 mole of this that we have. Excuse me. So we need to find our moles, because this is the way that stoichiometry works. Things react based on amounts. So here we don't have, we're not starting with a molarity, we're starting with a mass, which means then that we have to divide by a molar mass to get to our number of moles. This comes from our balanced equation, right? 2 moles of nitric acid for every 1 mole of magnesium hydroxide that we need. And then here is our molarity that we're using. So 5.00 grams times 1 mole times 2 moles times 1 liter divided by 58.320 times 1 times 0.500, right? This is our concentration. We've just flipped it over so that our units will cancel. So then this tells us that we need 0.343 liters of nitric acid with a concentration of 0.500 molar to titrate to neutralize all of this magnesium hydroxide. So it says for milliliters, so we just simply convert this back and see that this is 343 milliliters of solution is needed for this neutralization reaction.